Hello everybody, my name is Piotr Koziuk. You can call me Peter. I'm the product manager here at Comcores, as Daniel mentioned, and today's webinar is all about Interlaken. And the title is such because I believe it's a very good protocol for maximizing the usage of your throughput, of your links throughput. So this is how to unlock your chip's full data transfer potential with Interlaken. And shortly about Comcores, an introduction to the company. We have a mission of providing the best-in-class IP cores to help our customers build fantastic projects and products. Our solutions are silicon agnostic for ASIC, FPGA and others, and we hope to drastically reduce the cost and risk for our customers. We stand on 3 legs. The chip-to-chip interfaces, which are JSD204 and Interlaken, the wireless and front-haul solutions, so CPRI, ROE, and Ethernet subsystems for 5G, and also Ethernet solutions, so we have switches and MACs, also time-sensitive networks and MAC6, all that kind of super fun stuff. But today we're going to talk about Interlaken. And about myself, I've been working as a digital designer for over 10 years now. I've been implementing chip-to-chip IPs and mostly on the JSD204, which is sort of a standard to transfer data to converters. I've been leading a team of engineers as a technical lead and then advanced to product management on Comcores portfolio. I'm also a member of JEDEC, the standardization committee, and actually we're standardizing now the JSD204D. But that's beside the point. Today we're talking about Interlaken, and I would like to tell you a little bit about its purpose and history and how it evolved from XAUI and SPI. So in 2006, back then, if you remember, XAUI was sort of limited in the amount of lanes it could support, and it was sort of like meant for streaming of or sending serialized data, but it didn't have features like flow control or channelization or things like that. So the lackings of XAUI led 2 companies. It was Cisco and I'm falling short on the name. They formed a committee to find the perfect solution for the problem and came up with Interlaken. And Interlaken sort of took the best of both worlds and merged serializing of data with SPIs, flow control, and channelization. So Interlaken can support multiple channels, so data is interleaved from different sources onto the same links, and it has some pushback features for for doing flow control basically, but also is using high-speed serial lanes, so it minimizes the amount of pins that are required to transfer the data. So that was the base of the standard, and with years going by, the committee introduced extensions to the standard. The first one was actually a Aside extension, which was basically a simpler version of the protocol. So it didn't really provide as many channels, but the burst could be shorter and was very good for talking to devices like a Lucaside coprocessor or things like that, or sending short commands over the protocol. And Lucaside is not really compatible with base Interlaken. It's like a lightweight version. You can think of it as a lightweight version of Interlaken. Then in 2010, they introduced the Retransmit extension, which basically allowed the protocol to handle data failures on the links. So if data was deemed erroneous by failing a CRC check, the receiver could ask the transmitter to send the data again and recover from the error without involving the top-level sort of CPU or upper-level control features of the design. So it was sort of handling it on its own. Another extension for dual calendar, and this has to deal with flow control. So it introduced a second set of flow control sort of configuration, which you could change while the other one was running. And you could re-provision channel bandwidth or change priorities and things like that with that. And finally, recently in 2016, well, maybe not so recently, but they introduced the RS FEC extension, which is basically a read Solomon forward error correction. And this was sort of introduced because of PAM4 signaling and the bit error rates that are associated with PAM4. So to help the bit error rate, the RS FEC encoding or forward error correction is sort of fixing errors on the stream and improving the bit error rates to a usable above 10 to the minus or below 10 to the minus 15 ratio, right? And this is important when you're using PAM4 signaling over NRZ, because that is inherently like much poorer quality because of the 4 levels of signaling. And I'm going to talk briefly about features of the standard, so that if you're going to work with it, you'll have somewhat of a understanding of what's going on or what are the pros and cons to use it. So we talked a little bit about channels and allocations of channels into lanes. So Interlaken has a flexible number of lanes that it can map data onto, which is really fantastic. And it can map onto those lanes data from multiple different channels. And these channels can have different bandwidths. It can be very high-speed data or very sparse data like control data or some other. And Interlaken will take care of merging those data packets together and sort of sending them on a set of common lanes. And the encoding there is 64B, 67B. It's a little bit odd, but at the time it was cutting edge, I believe. So 64, 66 wasn't as well established, but this additional bit on top of the 66 has a meaning for it's an inversion bit, so it allows you to control the running disparity of the data. So there are 2 control bits and a inversion bit added on top of every 64 bits. And this data is mapped into bursts, so packets are split into burst-sized pieces to be sent across links. So there are 2 parameters that control the burst size in Interlaken. One of them is burst short, which defines the shortest burst that can happen. So it helps with processing multiple bursts at once inside of the design. So you control what is the smallest amount of the burst, and the burst max controls what is the largest size of the burst, and this helps with like retransmit buffer sizing or receiver buffer sizing, basically for processing this data. And we'll get to the diagram on the bottom in a second. I just want to mention also this look aside that I mentioned before. It is an alternative operation mode that has less channels and allows for shorter bursts, because in general, like in the basic Interlaken, the shortest burst is 32 bytes. But if you want to have shorter bursts, you can use this look aside mode, right? And then in this drawing, we have basically an indication of how data is mapped together with control words. You can see in these vertical columns, it's 67 bits, so basically 1 Interlaken word. There are burst control and idle control words, and also the B numbers are basically packet payload bytes. So here we're sending a packet of 70 bytes, but we have a burst max set to 64. So the payload doesn't fit into a single burst. And I wanted to demonstrate how the data is split into a second burst and what happens with the second burst if the data doesn't fill it completely. So in the headers in the orange and yellow, you can see different encodings for if it's a control word or a data word. And the burst control, there are specific bits that sort of have information about the burst. but I'll get into that later. It's followed by data, and after the burst max is reached, there will be another burst control word that sort of indicates data for the next burst. And once we fill all of the data, we'll start padding it with sort of fill bits. And once we fill into a whole Interlaken word, the next one will be an idle control word with an indication of an end of packet and how many bytes actually are filled in the previous word. And because the burst short is set to 32 bytes, you'll have to have padding for the next 3 control words just to sort of fulfill the burst short requirements before we start sending new data. And these sort of Interlaken words that are presented here can be mapped over a varying number of lanes, and they're sort of mapped in a round-robin fashion so that no single lane is unused or does not transmit data. So if you have active lanes, you will spread the whole data burst across all of those lanes. So on the bottom there are 2 examples of a 3-lane configuration and of a 2-lane configuration, indicating into which lane which Interlaken word will be split and sent. And that was a short introduction to the data mapping, and now I'm going to talk about data integrity aspect. And this is a very big part of Interlaken. So we have mechanisms for error detection, and we have a CRC24 which sort of covers the data burst, and inside of the burst control or idle control word there's space for a CRC, and the CRC covers the payload plus the control word, or the upper bits of the control word up to the CRC value, without those 67 or the 3-bit headers. And for the CRC32, this is a CRC that is sort of calculated on a per lane basis, because previously the burst is spanned across multiple lanes. So this is sort of like a data integrity CRC. The CRC32 is more of a diagnostic CRC to help you identify if a specific lane is acting up or has like a link fault, so you can quickly know which specific lane that is and maybe take it out of commission. And there's an additional CRC4 which is used for protecting out-of-band flow control, an out-of-band flow control interface, because it is a separate interface with separate pins that needs sort of a error detection mechanism as well. And besides the error detection, we have an extension for error correction, which is the RS FEC 544514, which is pretty common, I believe. It can correct 15 symbol bursts, so up to 141-bit long bursts of errors, and it's necessary when doing PAM4. And this error correction, the read-solve forward error correction mechanism, is sort of placed outside of the base Interlaken, so it's like an add-on which sits between the Interlaken and the PHY and does some recoding of 67 into 65 bits, and basically it aggregates data from 2 Interlaken lanes into a single FEC instance to calculate the parity, and also correct on the other end from a pair of lanes. So when using the FEC, you have to deal with a multiple of 2 number of lanes. And finally, the retransmit, which is a way of Interlaken self-correcting these errors, they occur. So if a CRC24 checker indicates that there's an error in the burst, in a data burst, it will ask to the transmitter through the out-of-band flow control for a retransmission. And how that happens, basically, the transmitter keeps in a transmission buffer a copy of the data that it has sent, some amount of data overriding it continuously. And at the point where the receiver will ask for a transmission, the transmitter will just basically stop the normal data path and start sending data out of the retransmit buffer. And it is the receiver's sort of role to find the point in a packet using some indexes where the error occurred, so the last known good burst, and pick up the transmission from there. And in that way, it can recover from error occurring on the transmission lanes, basically by the transmitting sending everything over again and the receiver picking up whatever it needs from that traffic. And now I've talked a lot about the flow control, and maybe now I'll go into more details of it. So Interlaken has two mechanisms for flow control, which is quite interesting. One of them is in-band flow control, and this in-band flow control is used when you have a duplex implementation, right? Because it uses the data lanes and some bits inside of the control words to carry the flow control information, and it needs to be a duplex, a bidirectional link, so that the receiver has also a transmitter path to communicate to the other side flow control information. If you are doing a simplex type operation where you only have a transmitter and a receiver on both ends, so one side can only transmit, you would use the out-of-band flow control interface, which is a set of separate pins that can communicate from the receiver to the transmitter the flow control information. And the flow control information is basically a 1-bit on-off sort of indication, plus some CRC that protects this data. The dual calendar extension we mentioned before also deals with flow control. So normally the set of on and off bits is called a calendar, and with dual calendar you keep a second copy of that, and it's called a shadow one. So there's an active one, and then there's a secondary that's a shadow one that you can modify while the link is operational, and then at a single instance in time switch the active for the shadow, so basically change the configuration while it's running. And finally, a very important part of Interlaken is rate matching, so the ability to slow the transmitter down in order to run at the speed of the receiver or the receiver's interface. And in this example here on the bottom, you can see we have an upstream device that has a 24 gigabit per second Interlaken sort of interface, and then a secondary interface device that interfaces between Interlaken and maybe two SPIs, and those SPIs will be running 10 gigs, so they have a total bandwidth of 20. And it would be sort of the designer's role to know that you need to sort of match these if you don't want flow control to kick in, to match these rates by setting up some registers, so you can instruct the upstream device to only use 20 of those 24 gigs of bandwidth, basically inserting some idle control words into these bursts, right? And another example is if you just have an application interface that is running slower, you can also limit the upstream device, right? And now, where can we use Interlaken with all of those fantastic features? Well, it has many uses because it's a very flexible protocol. It has many uses: high performance computing, network packet processing, in general networking like traffic management, switch fabric, communicating with memories, serial memories, or ternary content addressable memories, for FPGA, communicating with an FPGA, or in general wherever you have distributed processing. Interlaken is really useful, and it can take many shapes and sizes, so you can use it for all different types of applications. And finally, what Comcores, our company, can offer is we have an Interlaken IP core with extensions. We have an RTL test bench that we deliver with generally every of our IP cores that allows you to get a good start instantiating the IP, doing some testing, and this specific test bench has also some randomized testing features, like a very deep testing feature implemented for it. We also have a UVM-based test bench for if you want to get more into testing and security, or feel good about our solution. So we have a UVM test bench, we have an integration environment for that. We have a hardware test platform where it's basically an FPGA evaluation platform where we instantiated our Interlaken and Exciting Interlaken and did interoperability between the two protocols or two implementations. And we have a very responsive support to reduce your risk and cost. So you can always ask questions to our engineers directly through our support portal. We offer Interlaken training, and we use Jira for the service desk. And finally, I mentioned before that we had interoperability tested our Interlaken solution with the Xilinx design, so we feel very good about its quality and the features that we implemented. Right. And one more thing is we also like to work with our customers to customize our designs. So if there are any customizations you need around our design, like change of interface or adding features or changing whatever, we're open to that, and we always work with our customers to get the best possible solutions for them. So this would be it for my presentation. I hope it was very informing, and if you would like to know more, please contact us at sales@comcores.com or have a read of our white paper on Interlaken. There's more information there. And it was really nice talking with you guys. And I know that you probably submitted some questions in the chat, so now it would be a good time for me to answer some of those. Daniel?
Thank you, Peter. Excellent presentation. We do have questions. So the first question is, on slide 4, you mentioned burst short and burst max. What are the practical limits for burst sizes?
Right, so burst short and burst max are defining the sizes of burst, and burst short defines the minimum burst size, and it's 32 bytes in the standard protocol. But I just want to point out that it doesn't mean that the minimum amount of data you can put into a burst is 32 bytes. You can send a 1 byte packet if you need to, but the rest would be filled with padding. Right. On the opposite, burst max is not restricted by the protocol. In this example, is 64, but it can be a multiple of 64 bytes. So the sky is the limit. Usually the limitation comes from the controller implementations, especially if the controller is using store and forward mechanisms, where it needs to cache the entire burst before forwarding it out. Then the controller's sort of buffer would place a limit on the burst max. However, our controller has no such limitations.
Another question, what is the real performance of the protocol? What percentage of raw bandwidth is available for data payload?
Okay, so that is a very technical question, but let me try to sort of get into it. I think like if you look at the encoding itself, which is 6467B, encoding there is like a fixed sort of penalty for encoding, which is around 95.5%, just because of the free extra bits that you add onto your link. Then there are other factors that sort of are variable. So you have in this picture on top, you can see there's a meta frame, which basically carries some synchronization, some skip words, some diagnostics around the payload. And depending on how often or how big the meta frame is, so how often you insert these extra sort of meta frame bits, then they sort of the penalty and the throughput can be different. Let's assume like maybe a common one is 2K bytes or 2K words, sorry. So every 2000 clock cycles you would insert this, then that would be like negligible, like 99.8%. Of course, it can be 256 cycles or more. So depending how wide you set the meta frame, there's a penalty there. There's a penalty in the alignment efficiency. So here we saw in the slide some padding. So you have padding in your bursts that will sort of cut down on your throughput as well. But if you look at the best case example, so if you don't have any padding, then it can be 100%. Like I'm going to indicate the best case scenario, of course, it can go downhill from there. And finally, there's a framing efficiency. So depending on how big your bursts are, right, you will have these burst control words taking some of your bandwidth. So let's say your bursts are 256 bytes, so 4 times larger than here, then it will be like around 96, 97% penalty there. But in total, I think, like if you sum all of these up, the best case scenario is like 92 and a bit percent. So let's call it a 92% performance out of your throughput. Of course, you know, there are factors that play into it, but we get this question quite often, so we done this calculations a couple of times. I think it's a very good question.
Another question, on slide 7, you mentioned that for each channel there is 1 bit of status that is sent through flow control interface. Is this information transmitted continuously or only on request? And are status bits always transmitted from all channels, or can you send status bits only from selected channels?
Right. So the flow control information is being sent continuously, but you don't have to send all of it, right? So it always starts from channel 0, and it's sent in sort of 16-bit increments or 16 channel sections. So you start from 0 up to 15 and then 16 up to 31. But there's a sort of, you can see in the yellow on the top right here, a reset calendar bit that indicates you're starting over. And both of the in-band and out-of-band have sort of this indication that you're starting from 0. And that way you can sort of limit the amount of channels that you're sending flow control information for to the channels that you're actively using. So you can maybe have configured a large amount of channels. I think our solution can go up to 2000, but maybe you want to actively use 16. So then you can roll over every time with only the 16 control bits. So every time starting from 0.
Okay. Another question, can this protocol transfer data from multiple channels simultaneously, or does one channel have to end its transmission for another channel to start its transfer?
Okay, so you can see these bursts that are happening for a single packet. Basically, Interlaken is optimized to operate by interleaving these bursts together. So if you have a very long packet, or let's say 2 very long packets, you can send a section from one and a section from the other and a section from the one again and interleave them with each other, so that one is not waiting for the other to finish. So if that answers the question, basically you can send multiple channels, interleave that sort of more or less at the same time.
Yeah, that answers it. Another question, what makes Interlaken ideal for scalability and reuse? You know, why should a company use Interlaken?
Okay, so scalability, I think the fact, okay, so it has a flexible number of channels and a flexible number of lanes, so it can be a big solution or a small solution. So that's a plus. It's not and the protocol is not really dependent on the number of channels. As you can see on the bottom here, I indicate it can run 3 or 2, but it can also run 48. Like our solution can run up to 48 lanes in a single IP, and you know that sort of makes it scalable. Let's say scalable, right? With a single protocol, you can send data from multiple sources. So each of these channels can be tied into a different source type. One that is sending a lot of data, one that is very sparse and sends data very rarely. But you know, the protocol will combine them over the same set of lanes, and it can be used for these different types of traffics. But I think the key is that it's flexible enough that it can be used in different types of applications. So its reusability is very high. If you use Interlaken once, you'll definitely find a way to use it again in a different project, and carry on with. It can be a flexible tool for your toolbox. So it's highly reusable that way.
Oh, good. Final question. What is the availability of the Comcores Interlaken Solution?
Okay, so our IP is available off the shelf right now. If you just want to pick it up, then please contact sales@comcores.com and get in touch with our salespeople and talk to them like commercial terms. But yeah, it's ready to go. If you need it, it's there.
Great. Thank you very much, Peter, for your time. Excellent presentation and excellent Q&A.
Thank you, everybody. Have a great day.